This is the luckiest maths teacher in the world. Thank you so much for tuning in to this video in which we'll go through 3 applications of matrices: cryptography, encoding a message, polynomial interpolation, and the matrix exponential. So let's start with cryptography. So how would we encode a message using matrices? Well, we'll start with a simple message. I'm just going to write a nice one here. I love you. What we do is we take each letter and identify it with a number. A is 0, B is 1, C is 2, all the way up to Z, which is 25. So I've just written there a string of 8 numbers that represents our message. So what we need is a coding matrix. We're going to multiply this coding matrix by the numbers in our message. So we need this coding matrix to be invertible because the person receiving the message needs to be able to reverse the process and decode the message. Otherwise, there's not much point sending them a message. So I'm going to choose a 3 by 3 coding matrix here, A. Note, of course, you could choose one that's 2 by 2 or 4 by 4. It has to be a square matrix, as only square matrices are invertible. So this is my matrix here. Now we need to put the message into a matrix. I'll call that matrix B. So it's just going to have all the numbers from our message. Now because A is a 3 by 3 matrix, B needs to be a 3 by something. It needs to have 3 rows. So what we do is we go down. So we'll go 8, 11, 14, and so on. So what will happen though is we'll see there are not quite enough letters in our message. There are only 8 letters and that's not divisible by 3. So what we might do is add a Z on the end in the hopes that the person receiving the message will understand to ignore that. So now B is a 3 by 3 matrix and I can multiply A by B and I'll get a whole heap of other numbers and it will turn the message into gibberish. So if we multiply A, B together, we get this matrix here. So how are we going to turn this matrix into a sequence of letters? What we need to do is we need to reduce each of the elements of the matrix modulo 26. So for example, 80 is equivalent to 2 modulo 26, because when you divide 80 by 26, the remainder is 2. Of course, we're doing modulo 26 because there are 26 letters in the alphabet. So similarly, 163, if you divide that by 26, the remainder is 7. So that will be our next element. So this will start with 2 and 7, and we do the same for all 9 elements in the matrix. You can use an online modulo reduce calculator if you want, and this is what we should get. So then, of course, we just reverse our very first step and we change this back to letters. So like 2 represents C and so on. And we get this 3-letter word here that is complete gibberish. And that's the point of cryptography. We make it a gibberish message so that anyone who intercepts it really has no idea what we're trying to say. But the person for whom it's intended, they should have our original matrix A and they'll be able to decode it. So let's look how we would try to decode this message. So we'd start here with our message and we then turn it into this matrix here. What we're going to do is multiply the inverse of A by this matrix, but there's a slight twist because we had everything reduced modulo 26. So let's first figure out A inverse. So here we have A inverse. Now A is clearly invertible, but there's a problem here, this 1 over 75. It means most of the entries in this matrix, in this A inverse, are actually fractions, not whole numbers. Now this is a problem because we need to end up with whole numbers modulo 26 in order to turn them back into letters. But of course, there are no such thing really as fractions modulo 26, so we need to find a way to get around this. So the reason there are no fractions in modulo 26 is we don't have division. We can't divide by 75 in modulo 26. And I hope you also know that 75 doesn't really exist at modulo 26. 75 is actually equivalent to 23. modulo 26. So what we need to do is we need to find a way around dividing by 75. What we actually want to do is times by the inverse of 75 modulo 26. Of course, because 75 is equivalent to 23, in modulo 26, we can find the inverse of 23 modulo 26. And it's usually easiest to write this in a smaller way as minus 3. So 75 is equivalent to minus 3 modulo 26, because you need to add 3 to get the next multiple of 26. So what can I multiply by minus 3 to get 1 modulo 26? Well, note minus 3 times minus 9 gives you 27, or 1 modulo 26. So minus 9 is 17 modulo 26. So it turns out the inverse of both 75 and 23 modulo 26 is 17, because 75 times 17, which is also 23 times 17, or minus 3 times 17, is equivalent to 1 modulo 26. So if you're really stuck, there's online calculators that can help you calculate the inverse modulo 26. So what we do for A inverse is, instead of dividing by 75 like we normally would, we're going to multiply each element in the matrix by 17. I just want to digress a second to let you know that this is only possible because 75, the determinant of the matrix, had an inverse, modulo 26. If you had A with a determinant, say 2, you'd have 1 over 2 out the front, because when you're calculating the inverse matrix, you always have 1 over determinant A out the front. Now, because 2 doesn't have an inverse, modulo 26, you wouldn't be able to do what we're doing. Be able to replace dividing by 2 with multiplying by something else. So for that reason, the determinant of A, the coding matrix, needs to be a number that's co-prime to 26 so that it has an inverse modulo 26. So that, of course, limits our choices for matrices. What some people will do is they will actually use the 26 letters and then introduce 3 more characters. So like spacebar might be 27, exclamation mark 28, maybe the and symbol or the at symbol is 29, so that when you have 29 characters, because 29 is prime, every number less than 29 is co-prime, so it doesn't matter what the determinant is, as long as it's not a multiple of 29. That would yield more choices for the coding matrix and make the code more secure. Okay, let's get back to what we're doing here. So for A inverse, I'm going to multiply each inside the matrix by 17 and then reduce it modulo 26. And this is what I should end up with. So I put a star here just to indicate that it's not what A inverse actually is. We've just done a few things to it. So it is this matrix that I multiply by this to get the original message. So if I multiply this matrix here by this matrix here, I get this. So once again, I've got a matrix with very large numbers, but if I reduce this modulo 26, I reduce each element in the matrix modulo 26, I end up with what I started with, my matrix B, 8, 21, 14, and so on. And of course, you could just turn that back to letters and you get the original message of I love you. So it's not as straightforward as just applying a matrix and then multiplying by its inverse to decode. But overall, it is an easy system for somebody to encode a message and the intended recipient to decode, yet it would be very hard for someone who intercepted the message to decode without knowing the matrix A. All right, let's look at the second application. We're going to go through polynomial interpolation. So a polynomial is like a linear combination of positive integer powers of x. So it can be written as something plus something times x plus something times x squared plus something times x cubed, and so on and so forth. So the largest power of n is called the degree of the polynomial. So for polynomial interpolation, what we do is we have a set of points and we want to find a polynomial that goes through those points. It turns out that as long as the x values of the points we're given are not repeated, you will always be able to find a polynomial of degree n minus 1 that passes through those points. So let's illustrate this with an example. So I've written on the screen 4 points. So we can find a polynomial of degree 3 that passes through these 4 points. So that means we're finding a cubic that goes through them. And note that's possible because none of the x values is repeated. How do we find the equation? Well, because there are 4 points, we know that the polynomial we're going to fit is of degree 3. It's going to be a cubic. So we can write it as y equals ax cubed plus bx squared plus cx plus d. So what we have to do is find the coefficients a, b, c, and d. And it turns out we find them through a system of linear equations. What we do is we substitute each point one by one into this equation in yellow. So if I substitute the point minus 4, 5, what that means is I change y to 5 and x to minus 4. So I get minus 64a plus 16b, substituting x for minus 4, minus 4c plus d. Let's do the same with the second point. I'll substitute this and I get y equals a x cubed, so x cubed will be minus 2 cubed, which is minus 8, plus 4b minus 2c plus d. That's another equation. So let's do the same for the other 2 points. This highlights why we can always fit a polynomial of degree n minus 1 to a data set of n points, because a polynomial of degree n minus 1 will have n coefficients. You're solving for those n coefficients, and n points means n equations. So as I said, this will work as long as the x values aren't repeated, because if they were, then the matrix we would have wouldn't be invertible. So we'll turn this into a matrix and row reduce it. This is our matrix equation, and all we need to do is augment and row reduce the matrix, and we get this. So, of course, this tells us the solution is A equals 1, B equals 4, C equals minus 1, and D equals 1. So how easy is that? We have found the answer. We have found the cubic that goes through this point. It is just y equals ax cubed plus bx squared plus cx plus D. How easy is that? So let's look at the last application we're going through, which is the matrix exponential. So we're not going to go too deep into the matrix exponential because that would require a lot of calculus, and this course doesn't really assume that you have a lot of calculus. So we're interested in this number e again, such an important number in maths. So it's approximately 2.71828 and so on, goes on forever. It's an irrational number. It can be defined as the limit as n approaches infinity of 1 plus 1 over n to the power of n. It's so important for so many reasons, not least of which is when you differentiate y equals e to the power of x, you get the same function back. So it's very important in differential equations as well. We're not going to go too much into the calculus, but because of calculus, there is a way that we can write e as a polynomial. So this is called its Taylor polynomial. E to the power of x is equal to 1 plus x squared over 2 factorial plus x cubed on 3 factorial plus x to the power of 4 on 4 factorial, and so on. It goes on forever. That's the only way you could have, a whole heap of fractions like this adding up to give an irrational number. This sequence never ever stops. So this, as I said, is its Taylor polynomial. This comes about due to calculus. We're not going to go too much into the calculus, however. Just in case you're not aware, this exclamation mark means factorial. N factorial is the product of all the positive integers all the way up to n. So what does this have to do with matrices at all. Well, actually, sometimes we need to calculate e to the power of a, where a is a matrix. Now, because we're talking about powers here, x to the power of 2, x to the power of 3, and so on, a will need to be a square matrix. Because, of course, you can't take powers of a matrix that's not square. So, to write e to the power of a, where a is a matrix, we're going to take the same formula here, just replace x with a matrix A. So we have e to the a equals 1 plus a squared on 2 factorial plus and so on. In sigma notation, this would be written as the sum from I equals 0. We start the 0th term to infinity of a to the power of I over I factorial. Note that 0 factorial and 1 factorial both equal 1. So, of course, e to the power of a, where a is a matrix, will return another matrix. It turns out that this always gives you an invertible matrix. Even if the original matrix A is not invertible, e to the power of a is invertible. So this is very important in differential equations. As I said, we're not going too much into the calculus, though. So you might be thinking, well, hang on a minute, why is there a 1 in the Taylor series for the matrix A? Well, what we're going to do to make this work, because you can't add a scalar to a matrix, what we do is we write this as I, because that's basically the matrix equivalent of 1, and it's also a to the power of 0. So, of course, when I say I mean I that is the same size as a. We're going to look at an example involving calculating e to the power of a, and I've picked a really easy example. Of course, the matrix exponential of a is very hard to calculate because there are an infinite number of terms. Eventually, if you're doing it by hand or with a computer, you're going to have to stop, and you often need to use a lot of terms so that you're close to the actual answer. But there are some times when you only need to use a few terms, and we're going to look at one of those times. So let's let A be this matrix on screen. The reason that we're only going to need a few terms to calculate the matrix exponential is that this matrix is actually nilpotent. A to the power of 3 actually gives you the 0 matrix. So in the sequence of terms, all of these terms here and all these terms here, they will be 0, because if a to the power of 3 is 0, all subsequent powers of a will be 0. So we only need to calculate this here. We only need to calculate I plus a squared over 2 factorial. And here we have our answer for the exponential of a, and that was pretty easy to calculate with or without technology, but in general it's something we need technology to do. Alright, thank you so much for watching this video. This has been the luckiest maths teacher in the world. Have a great day.